Tonight we are going to talk about a planet astronomers have stared at for more than a decade without explaining a single thing about it. It was photographed directly back in 2013, its own light captured in an image. And from that first photograph, it looked wrong. A strange, unmistakable shade of pink, a colour no planet should have. For over 10 years, every attempt to explain that colour failed. The biggest telescopes on Earth pointed at it for entire nights and came back with nothing usable. Then, this year, the most powerful telescope ever built turned toward it, and in roughly 2 hours did what a decade of effort from the ground could not. It found an answer. And the answer is not what anyone expected. By the end of tonight, you are going to understand why this planet turned pink, and why scientists still cannot agree on whether it is a planet at all. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why this planet has been such a stubborn mystery, you need to understand how it was found in the first place, because the method itself is unusual. Most of the thousands of exoplanets discovered since the 1990s have never actually been seen. They are detected indirectly by watching a star's light dim slightly as a planet passes in front of it, or by measuring a tiny wobble in a star's position caused by the gravitational tug of an orbiting planet. These methods are powerful, but they give you numbers, not images. A transit tells you a planet's size relative to its star. A wobble tells you a planet's mass and orbital period. Neither one shows you the planet itself. Direct imaging is different, and it is far harder. A planet is staggeringly faint compared to the star it orbits, often 1 billion times dimmer or more. Trying to photograph a planet next to its star is like trying to photograph a firefly sitting directly next to a lighthouse beam from miles away. The lighthouse drowns out everything. As of the early 2010s, only a small handful of exoplanets, fewer than 30 out of nearly 1,000 confirmed at the time, had ever been captured this way. In 2011, a team of astronomers using the Subaru Telescope, an 8.2-metre instrument sitting atop Mauna Kea in Hawaii, pointed its high-contrast imaging instrument at a star called GJ 504, also known as 59 Virginis, a sun-like star sitting roughly 57 light-years away in the constellation Virgo. The instrument they used, called Hikiau, combined with an advanced adaptive optics system, was specifically built to suppress the overwhelming glare of a host star and tease out anything faint orbiting nearby. In the resulting images, the team found something. A faint point of light, separated from its star by a wide gap, persisting in observations taken a year apart in a way that ruled out the possibility it was simply a background star coincidentally aligned in the same direction. By 2013, the discovery was confirmed and published. A real planet, or something very close to one, captured directly in its own light, orbiting a star not unlike our own Sun. The team nicknamed it a second Jupiter, and almost immediately, something about it stood out. Its colour. When the astronomers examined the planet's light more closely, they found it carried an unmistakable rosy-magenta hue, a deep pink unlike anything seen in any other directly imaged planet before or since. One of the Discovery team's co-authors at NASA's Goddard Space Flight Center described it vividly. If you could travel to this giant planet, you would see a world still glowing from the heat of its formation with a colour reminiscent of a dark cherry blossom, a dull magenta. The pink planet had a name from that moment forward, and a mystery that would take more than a decade to crack. To understand why a pink planet is genuinely strange, and not just a curiosity, you need to understand what actually determines the colour of a gas giant world. A planet's apparent colour comes from the interaction between the light arriving from its star, or in the case of a young, still cooling planet, the planet's own internal heat, and the chemistry of its atmosphere. Different molecules and particles absorb and scatter different wavelengths of light. Methane, for instance, strongly absorbs red light, which is why Uranus and Neptune, both methane-rich worlds, appear blue and cyan. Clouds made of different compounds scatter light differently depending on their composition, their altitude, and the size of the particles that make them up. Jupiter's bands of orange, brown, and white come from a complex layering of ammonia ice clouds, ammonium hydrosulfide clouds, and deeper water clouds, each absorbing and reflecting sunlight differently, further complicated by chemical reactions driven by the planet's own internal heat and ultraviolet light from the sun. By the time GJ504b was discovered in 2013, astronomers already had a reasonably well-developed framework for predicting how a young, hot gas giant should look. Most directly imaged exoplanets glow with the residual heat of their own formation, since they are typically very young, recently formed, and still radiating away the energy released when they coalesced from a collapsing cloud of gas and dust. These young giants tend to be extremely hot, with temperatures often between 1000 and 2000 degrees Fahrenheit, hot enough that their atmospheres glow with a reddish or orange thermal emission, similar to the way a piece of metal glows when heated. GJ504b broke this pattern from the very start. Its temperature, measured at around 550 degrees Fahrenheit, roughly the temperature inside a bread oven, was dramatically cooler than nearly every other directly imaged planet known at the time. This made it by a wide margin one of the coldest planetary mass objects ever directly photographed. And cooler planets are supposed to develop thick cloud layers, since lower temperatures allow more compounds to condense out of the atmosphere into cloud particles. The same basic physics that causes water vapour to condense into clouds here on Earth as air cools. Thick clouds typically make a planet's spectrum harder to read, but tend to produce more muted, greyish or whitish colours as light scatters broadly across all wavelengths rather than being selectively absorbed. Instead, the planet's colour came back distinctly pink, and its early near-infrared measurements suggested something else unexpected. Its light appeared bluer than other young giant planets, which researchers interpreted as a sign of a relatively clear atmosphere with fewer clouds than expected for an object this cold. A cold planet that should have thick clouds, but whose early data suggested it might have thin ones. A planet whose temperature said one thing and whose colour said something else entirely. The contradiction sat there, unresolved, for more than a decade, because no instrument available at the time could gather enough light from an object this faint and this cold to settle the question definitively. For more than 10 years after its discovery, GJ504b sat in a strange scientific limbo. Astronomers knew it existed. They had a rough estimate of its mass, its temperature, its orbit, and its distinctive colour. But every attempt to go deeper, to actually break its light apart into a full spectrum and read the specific chemical fingerprints hiding within it, ran into the same wall. The planet was simply too faint and too cold for any ground-based telescope to extract a usable signal. This is worth understanding properly, because it explains why the eventual breakthrough felt so dramatic to the scientists involved. Capturing a planet's spectrum requires far more light than simply photographing it as a point source. A direct image just needs enough photons to register a faint blob against the noise. A spectrum requires spreading that already faint light out across a range of wavelengths, which means each individual wavelength bin receives only a small fraction of the total light collected. For a bright, nearby hot planet, ground-based telescopes equipped with adaptive optics can sometimes manage this, given enough observing time. For a planet as cold and dim as GJ504b, the challenge multiplies. Lead researcher Aneesh Baburaj, a postdoctoral associate at Northwestern University who led the eventual breakthrough study, later described just how badly earlier efforts had failed. In the past, other astronomers observed the companion for an entire night with some of the biggest telescopes in the world to obtain a spectrum, and they could not see the object. Read that again slowly. An entire night on some of the largest, most sophisticated telescopes ever built on the surface of the Earth, pointed continuously at a single target, and the planet simply did not appear in the resulting data. Not partially, not faintly. It could not be seen at all. This was not a failure of effort or skill. It was a fundamental limitation of trying to do this kind of observation from underneath an atmosphere, even with the best adaptive optics correcting for atmospheric distortion. Earth's atmosphere itself glows faintly in infrared wavelengths, the same wavelengths where a cold planet like GJ504b emits most of its light, adding background noise that ground-based telescopes cannot fully eliminate no matter how large their mirrors or how sophisticated their instruments. A planet's planet mass companion this cold, this faint, sitting this close to the overwhelming glare of its host star, was for all practical purposes unreachable using any technology available before 2022. The mystery did not persist because nobody was trying. It persisted because the tools required to solve it had not yet been built. The James Webb Space Telescope changed the equation entirely, and understanding why requires understanding what makes Webb fundamentally different from every ground-based observatory that had tried and failed before it. Webb sits roughly 1 million miles from Earth, far beyond any atmosphere, in the cold vacuum of space, where its instruments are shielded from the sun by a tennis court-sized sunshield and cooled to temperatures near absolute zero. Without an atmosphere glowing in infrared light directly between the telescope and its target, and without the constant atmospheric turbulence that ground-based adaptive optics must continuously correct for, Webb can achieve a level of sensitivity in infrared wavelengths that no telescope on Earth's surface can match, regardless of mirror size or technological sophistication. A team led by Baburaj at Northwestern University, working alongside collaborators from the Space Telescope Science Institute and a long list of institutions across the field, secured observing time on Webb specifically to attempt what a decade of ground-based efforts had failed to achieve. Using Webb's coronagraphic instruments, designed specifically to block out the overwhelming light of a host star while preserving the faint signal of anything orbiting nearby, the team isolated GJ504b's light from the glare of its parent star and captured something no one had managed before: a clean, detailed spectrum. The difference in results was not incremental. It was total. What had taken countless failed observation attempts from the ground, full nights on some of the largest telescopes on Earth producing nothing usable, was accomplished by Webb in roughly 2 hours. 2 hours, compared to more than a decade of accumulated failed effort. The spectrum Webb returned was rich with information. It showed clear signatures of water vapour, methane, carbon dioxide and ammonia in the planet's atmosphere, the kind of basic molecular fingerprint astronomers expect to find in a cool gas giant. But when the team tried to model the full spectrum using only these gases, the fit was not quite right. There were inconsistencies, places where the predicted spectrum and the observed spectrum diverged in ways that simple atmospheric chemistry alone could not explain. Something else was shaping the light before it ever reached Webb's detectors. Something the team had not initially built into their models. The mystery that had defeated astronomers for over a decade was not fully solved by simply getting a clearer signal. The clearer signal revealed a deeper puzzle hiding underneath the original one. And the answer to that deeper puzzle is what makes this story genuinely remarkable. Here is what the team found when they finally accounted for the missing piece. The molecular gases alone, water vapour, methane, carbon dioxide, ammonia, could not fully explain the shape of the spectrum Webb had captured. The signatures of certain molecules appeared muted, suppressed, as though something was sitting between the deeper layers of the atmosphere where those gases existed and the upper layers where Webb's instruments were detecting light. The team began running simulations, testing different scenarios to see what could be producing this effect. They tried introducing clouds into the model, and they tested several different cloud compositions, candidates drawn from the established theoretical literature on what kinds of clouds might exist at this specific range of cold planetary temperatures. One configuration stood out clearly above the rest: clouds made of vaporized salt particles. When the team incorporated salt clouds into their atmospheric model, the inconsistencies disappeared. The fit between the predicted spectrum and Webb's actual observations became, in the team's own words, physically possible for the first time. Baburaj described the process directly. We ran simulations with clouds, and the results aligned with what we know about cold planets. We tried 3 different types of clouds, and salt clouds fit best. When we accounted for salt clouds, it subdued the signature of molecules hidden deeper in the companion's atmosphere. Then the results became physically possible. This was not a small or expected result. Scientists had theorized more than 15 years earlier that salt clouds could form in the atmospheres of cold planetary mass objects under the right conditions, but no one had ever directly observed clear evidence of them before. Baburaj's own reaction, reported afterward, captures how unexpected the finding genuinely was. We were very surprised, because people have theorized that salt clouds might exist in the atmospheres of companions at these temperatures, of say 500 to 700 degrees Fahrenheit, but people in general just don't observe any kind of signatures of clouds in such temperatures, so we were very surprised. The theory had existed on paper for over a decade and a half. Nobody had confirmed it in a natural observed planet, anywhere, until GJ504b's spectrum finally made it undeniable. The pink colour that had puzzled astronomers since 2013 finally had an explanation rooted in real atmospheric physics rather than speculation. Salt clouds, sitting in the upper atmosphere, scattering and filtering the light coming from deeper, hotter layers of the planet, reshaping the spectrum in exactly the way that had confused every previous attempt to model this world. The mystery was not that the planet had an unusual colour by accident. It was that the planet was hosting a kind of atmospheric chemistry nobody had ever directly confirmed before, and that chemistry was actively distorting the very signals scientists were using to try to understand it. It is worth pausing here to properly understand what a salt cloud in a planetary atmosphere actually is, because the phrase sounds almost domestic, conjuring images of a kitchen shaker, when the reality is a genuinely exotic atmospheric phenomenon happening under extreme conditions. On Earth, clouds form when water vapour in the atmosphere cools below a certain threshold and condenses into liquid droplets or ice crystals. The same basic physics behind every cloud you have ever seen drifting overhead. The same fundamental principle applies on other worlds, but the substance that condenses depends entirely on what is available in the atmosphere and at what temperature and pressure that condensation becomes possible. On a planet like GJ504b, with a temperature around 550 degrees Fahrenheit, far too hot for water to remain a familiar liquid or ice cloud in the way it does on Earth, but cool enough for other compounds to begin condensing out of the gas phase. At these specific temperatures, certain alkali metal salts, compounds involving elements like sodium and potassium combined with chlorine, can exist as vapor at higher temperatures deeper in the atmosphere, and then condense into solid or liquid particles as that gas rises and cools in the upper atmospheric layers. These particles form genuine clouds, structurally similar in concept to water clouds on Earth, except composed of an entirely different chemistry, suspended in an atmosphere of hydrogen and helium rather than nitrogen and oxygen, under pressures and temperatures that bear no resemblance to anything found naturally on our own planet's surface. These salt clouds sit at a specific altitude range in the atmosphere, a layer where the temperature happens to fall within the narrow window where the relevant salt compounds transition from vapor to condensed particles. Above that layer, conditions are too cool for the salts to remain in vapor form, but the particles that have already condensed can persist, scattering light passing through them. Below that layer, conditions are too hot for any salt particles to form or survive, so the gas remains in vapor form, mixed invisibly into the deeper atmosphere. The result is a discrete cloud deck, a layer of suspended salt particles sitting at a specific altitude, scattering incoming and outgoing light in ways that depend on the particle size, density, and composition of the cloud. This scattering is precisely what was confusing the spectral models for over a decade. Light coming from deeper, hotter layers of the planet's atmosphere, carrying the chemical fingerprints of water vapor, methane, and other gases, had to pass through this salt cloud layer before reaching Webb's detectors. The cloud particles scattered and absorbed portions of that light selectively, depending on wavelength, distorting the clean chemical signatures that astronomers were trying to read. Once the team's models accounted for this scattering effect, the previously confusing spectrum resolved into something coherent and physically consistent, finally explaining both the planet's distinctive pink colour and the decade of failed attempts to characterize its atmosphere from the ground. The salt clouds were not the only surprise hidden in Webb's data. As the team continued to analyze the spectrum, they found evidence of something else, a finding that adds a second, still unresolved layer to this planet's strangeness. GJ504b appears to contain an unusually large quantity of elements heavier than hydrogen and helium, the elements astronomers collectively refer to as metals, regardless of whether they behave like metals in the everyday sense. This metal enrichment is significant because it bears directly on one of the deepest open questions in planetary science: how giant planets actually form in the first place. There are two broadly competing theories. The first, called core accretion, proposes that giant planets begin as small rocky or icy cores, similar in some ways to the building blocks of terrestrial planets, which then grow large enough to gravitationally capture huge quantities of surrounding hydrogen and helium gas from the disk of material orbiting a young star. This process tends to produce planets enriched in heavier elements, since the initial solid core contributes a disproportionate amount of heavy material relative to the vast hydrogen and helium envelope that gets added later. The second theory, called gravitational instability, proposes that giant planets can form directly from the rapid collapse of a clump of gas within a young, massive protoplanetary disk, similar in some ways to how stars themselves form, just on a much smaller scale and without ever achieving the conditions necessary to ignite nuclear fusion. Planets formed this way are expected to have a composition much closer to the original gas cloud they formed from, with proportionally less enrichment in heavy elements compared to planets that grew around a solid core. GJ504b's unusually high metal content points toward the core accretion scenario, the same basic process believed to have formed the giant planets in our own solar system. But this creates its own puzzle, because GJ504b orbits its star at a minimum distance of roughly 44 astronomical units, comparable to the distance between our Sun and Pluto, an extraordinarily wide separation for a planet to have formed through core accretion, a process that is generally expected to operate most efficiently much closer to a young star, where the protoplanetary disk is denser and core formation can proceed more rapidly. Forming a planet with this much heavy element enrichment at this enormous distance from its star strains the standard core accretion model considerably. One of the original 2013 Discovery paper's co-authors, Dr. Marcus Janssen, made this point clearly even at the time of the planet's initial discovery, noting that the planet's existence implies astronomers needed to seriously consider alternative formation theories, or perhaps to reassess some of the basic assumptions in the core accretion theory itself. More than a decade later, with far more detailed atmospheric data now available, that same fundamental tension remains unresolved. The pink planet's salt clouds may finally be explained. Its origin story is not. There is a second equally fundamental question hanging over GJ504b that the new Webb data has not resolved, and it concerns what kind of object this actually is. Is it a planet? Or is it something else entirely? A small failed star known as a brown dwarf? This is not a trivial classification question, and the reason it remains unsettled for GJ504b reveals something important about how astronomers actually define the boundary between planets and stars in the first place. A brown dwarf is an object that formed the way stars form, through the gravitational collapse of a cloud of gas, but never accumulated enough mass to ignite the sustained nuclear fusion of hydrogen into helium that powers a true star like our Sun. Brown dwarfs occupy a strange middle category, too massive to be considered ordinary planets in the way most astronomers understand the term, but too small to become true. Hydrogen-fusing stars. The conventional dividing line between a giant planet and a brown dwarf is often set around 13 times the mass of Jupiter, the rough threshold at which an object becomes massive enough to fuse deuterium, a heavier isotope of hydrogen, even if it cannot fuse ordinary hydrogen the way a full star does. GJ504b's mass estimate has shifted dramatically depending on which set of assumptions astronomers use to calculate it, and this is where the story gets genuinely strange. The mass of a directly imaged object like this one is typically estimated using evolutionary models that relate a planet's brightness and temperature to its mass, given an assumed age for the system. But GJ504, the host star, has two wildly different age estimates in the scientific literature. One analysis suggests the system is extremely young, around 21 million years old. Another, using a different dating method based on the star's rotation and magnetic activity, suggests the system is far older, somewhere between 2.5 and 4 billion years old. These two age estimates produce dramatically different mass calculations for the planet. If the system is young, GJ504b's mass comes out to roughly 1.3 times the mass of Jupiter, comfortably within ordinary giant planet territory. If the system is old, the same brightness and temperature measurements imply a mass of roughly 23 times the mass of Jupiter, solidly within brown dwarf territory, comparable to current estimates putting it around 25 times Jupiter's mass. The new Webb observations, while resolving the salt cloud mystery, lean towards supporting the older age estimate, based on the planet's relatively cool measured temperature and astronomers' improved understanding of how planetary mass objects cool over time. A planet this cool, the team reasoned, has likely had billions of years to radiate away its formation heat, consistent with the older age scenario and the higher mass estimate. But Webb's spectrum, however detailed, cannot directly measure age. It measures the planet as it exists right now. The fundamental ambiguity, whether GJ504b is a true giant planet or a brown dwarf hiding under a planetary nickname, remains formally unresolved. Researchers are still uncertain whether the object formed like a planet or more like a small star. As the Space.com science writer Robert Lee put it succinctly after the Webb findings were published, that means astronomers aren't quite ready to determine if GJ504b is a gas giant planet or a brown dwarf, or, as he wryly noted, should that be a pink dwarf? Let us turn our attention briefly to the star at the centre of this story, because understanding GGA 504 itself helps put the planet's strangeness into proper context. GJ 504, also catalogued as 59 Virginias, sits in the constellation Virgo at a distance of approximately 57 light-years from Earth, close enough by galactic standards to be considered a genuine stellar neighbour, though still far enough that its light left the star nearly 6 decades ago. It is classified as a G0 type star, placing it in the same broad spectral category as our own Sun, which is classified as G2. This makes GJ 504 only slightly hotter and slightly more massive than our Sun, a close enough match that astronomers often describe it as Sun-like, a description that matters because it means the planetary system orbiting GJ 504 formed under conditions reasonably comparable to those that produced our own solar system roughly 4.5 billion years ago. The star is bright enough to be visible to the naked eye under suitably dark skies, registering at approximately magnitude 5 in brightness, sitting right at the edge of what unaided human vision can detect from a sufficiently dark location, far from the light pollution of any city. This is part of what made the original 2013 discovery technically remarkable. The Subaru Telescope team specifically selected GJ 504 partly because its brightness allowed it to serve as what astronomers call a natural guide star for the adaptive optics system, providing the bright reference point of light the telescope's instruments needed to measure and correct for atmospheric distortion in real time, a technical requirement that made the extremely faint companion planet detectable in the first place. GJ 504b itself orbits its star at a minimum projected distance of roughly 44 astronomical units, an astronomical unit being the average distance between the Earth and our own Sun. 44 astronomical units is comparable to the average distance between our Sun and Pluto, placing this planet in a region of its system roughly analogous to the distant frozen outer reaches of our own solar system, far beyond where any of the 8 planets we know reside. At that distance, even though GJ 504 is similar in luminosity to our own Sun, the amount of starlight reaching GJ 504b is a tiny fraction of what Earth receives, meaning any heat the planet exhibits comes overwhelmingly from its own internal processes, whether residual formation heat from a young planet or the slower, longer-term cooling of a much older brown dwarf, rather than from warming by its distant host star. This is in fact precisely why GJ 504b's temperature serves as such an important clue in the ongoing age and mass debate. Since a planet this far from its star receives so little external heating that its measured temperature reflects almost entirely its own internal thermal history, the slow fade of heat accumulated either during a relatively recent formation or across billions of years of patient, gradual cooling. It is worth taking a step back here to appreciate why direct imaging, the method that found GJ 504b in the first place, occupies such a special place in the broader search for understanding worlds beyond our own solar system, because the implications extend well beyond this single strange pink object. As of the most recent counts, astronomers have confirmed more than 6,000 exoplanets across the galaxy, an extraordinary catalogue built almost entirely through indirect detection methods. The vast majority were found by the transit method, watching for the tiny periodic dimming of a star's light as a planet crosses in front of it from our point of view, a technique responsible for the bulk of discoveries made by missions like Kepler and the Transiting Exoplanet Survey satellite, A smaller but still significant number were found through radial velocity measurements, detecting the subtle gravitational wobble a planet induces in its host star's motion. Both methods are extraordinarily powerful for finding planets and measuring certain of their properties, particularly size and mass, but both share a fundamental limitation. They tell you a planet exists, they do not show you the planet itself, and they generally cannot directly probe its atmospheric composition without additional, more specialized follow-up observations. Typically only possible for planets that happen to transit their star as seen from Earth, a geometric coincidence that excludes the majority of known systems. Direct imaging sidesteps this limitation entirely, because it captures the planet's own light, whether reflected starlight or, more commonly for the kinds of young, hot or large planets imaging can currently detect, the planet's own thermal emission. Once you have that light in hand, you can do something transit photometry alone cannot easily achieve. You can spread it into a full spectrum and read its chemical fingerprint directly. The same fundamental technique that allowed Webb to identify water vapor, methane, carbon dioxide, ammonia, and ultimately salt clouds in GJ504b's atmosphere. This is precisely why the small handful of directly imaged exoplanets, despite representing a tiny fraction of the total exoplanet catalogue, punch so far above their weight in scientific importance. Each one offers a kind of atmospheric access that the vast majority of known exoplanets simply cannot provide using current technology. Webb's success with GJ504b, extracting a clean, detailed spectrum from one of the coldest, faintest directly imaged objects ever studied, in a fraction of the time that ground-based efforts had repeatedly failed to achieve even partial results, represents a genuine expansion of what is now scientifically possible. The research team explicitly noted that the same techniques demonstrated here could soon be applied to other cold, faint planetary mass objects whose atmospheres have remained largely inaccessible until now, suggesting that GJ504b's decade-long mystery, now substantially resolved, may have been less an isolated curiosity and more a preview of an entire population of similarly strange, similarly cold worlds finally becoming reachable for detailed study. Try for a moment to actually picture standing close enough to see this world clearly, since the Discovery team themselves have already attempted to describe it. Imagine approaching GJ504b after a journey of 57 light-years, far beyond anything any human spacecraft could realistically achieve, but worth imagining nonetheless. From a distance, the planet would not glow with the fierce orange-red thermal radiance of a young, hot gas giant the way many other directly imaged exoplanets do. Its colour, as the original Discovery team described it, would resemble a dark cherry blossom, a dull magenta, a deep and somewhat muted pink rather than a vivid, saturated one. This colouring comes from the combination of the planet's relatively cool internal heat glowing faintly in longer wavelengths, and the way the newly discovered salt cloud layer scatters and filters that light as it passes through the upper atmosphere on its way out into space. Approaching closer, the planet's enormous size would become apparent, with a mass somewhere between roughly 3 and 25 times that of Jupiter. Depending on which age estimate for the system proves correct, GJ504b would dwarf every planet in our own solar system except possibly the very largest brown dwarf scenario, which would put it considerably more massive than Jupiter, while likely still being similar in physical diameter. Since gas giants beyond a certain mass do not grow proportionally larger, their increased gravity instead compressing their interior more tightly, a genuinely counterintuitive property of giant planet physics. There is no solid surface to land on, the same as every other gas giant discussed in these long-form journeys through the outer worlds of our own solar system and beyond. The atmosphere simply thickens with depth, transitioning gradually from the visible cloud layers, including the newly discovered salt clouds, into increasingly dense and hot layers below, eventually compressing into exotic states of matter under pressures far beyond anything achievable in any laboratory on Earth. Winds in such an atmosphere are likely to be extreme, though their precise speeds and patterns remain unmeasured for this particular world, since the techniques used so far have focused on the planet's overall spectrum rather than detailed atmospheric dynamics. If you could somehow survive long enough to look up from within the planet's upper cloud layers, you would see the faint, distant point of light that is GJ504, the host star. Sitting 44 astronomical units away, a separation roughly equivalent to the gap between our own Sun and Pluto. From that distance, even a Sun-like star provides only the faintest illumination, a dim, cold daylight utterly unlike anything experienced on Earth, with most of whatever light and warmth exists in this distant world's atmosphere coming not from the star at all, but from the planet's own internal heat, slowly and patiently radiating away the energy of its formation. Whether that formation happened a mere 20 million years ago or more than 4 billion years in the past. GJ504b's uncertain identity, hovering somewhere on the blurred boundary between giant planet and failed star, connects to a much larger and genuinely fascinating population of objects scattered across the galaxy that astronomers have only begun to properly catalogue and understand over the past 3 decades. Brown dwarfs were first confirmed to exist in 1995, remarkably recently in the broader history of astronomy, when a team using the Palomar Observatory in California identified an object called Gliese 229b, orbiting a small red dwarf star, with a mass too low to sustain hydrogen fusion, but clearly too massive and too hot to be an ordinary planet. Since that first confirmation, astronomers have identified and catalogued many hundreds of brown dwarfs, and current models suggest they may be nearly as common throughout the galaxy as ordinary stars, simply far harder to detect given how faint and cool they generally are compared to actual stars. Brown dwarfs occupy a genuinely strange physical category. Unlike true stars, which settle into a stable equilibrium where the energy released by sustained hydrogen fusion in their core exactly balances the inward pull of their own gravity for billions of years, brown dwarfs never achieve this balance. They begin their existence hot, glowing with the residual heat released during their gravitational formation, similar in this specific respect to a young, still cooling giant planet. But unlike a planet, a brown dwarf typically did not form within the disk of gas and dust surrounding a young star. It is generally believed to have formed independently, through the direct gravitational collapse of its own clump of gas, the same fundamental process that forms stars, just on a smaller scale that fails to reach the threshold required for sustained fusion. Over time, ranging from millions to billions of years, brown dwarfs simply cool, fading slowly from a hot, glowing youth toward an increasingly dim, cold maturity, with no internal furnace to replenish the heat they continuously radiate away into space. This cooling trajectory is precisely what makes age such a critical and frustratingly difficult variable to pin down for objects like GJ504b. A relatively young, low-mass giant planet, and a much older, higher-mass brown dwarf can, under the right combination of circumstances, present nearly identical observed temperatures and luminosities, because both are simply objects radiating away stored heat, with the specific combination of age and mass determining exactly how much heat remains at any given moment. Distinguishing between these two very different formation histories and identities, using only a snapshot of an object's current brightness and temperature, remains one of the genuine, persistent challenges in the study of directly imaged exoplanets and brown dwarfs alike, a challenge that GJ504b embodies about as clearly as any object yet discovered. It is worth pausing to place the salt cloud discovery in a broader context, because the idea of exotic, non-water clouds forming in alien atmospheres is not unique to GJ504b, even though this marks the first time such clouds have been directly confirmed at these specific cold temperatures. Across the solar system, and increasingly across the broader population of known exoplanets, astronomers have documented an extraordinary diversity of cloud chemistry, each one a direct consequence of the specific temperature, pressure, and available chemical ingredients in a given atmosphere. Venus, our planetary neighbour, is permanently shrouded beneath thick clouds composed primarily of sulfuric acid droplets, a corrosive, toxic chemistry entirely unlike anything found in Earth's water-based weather systems, yet producing a cloud layer dense enough to completely obscure Venus's surface from any visible light observation. Jupiter's banded appearance comes from multiple distinct cloud layers stacked at different altitudes, ammonia ice clouds in the uppermost visible layer, ammonium hydrosulfide clouds in a middle layer, and water clouds deeper still, each layer corresponding to the specific altitude where temperature and pressure conditions allow that particular compound to condense out of the surrounding hydrogen and helium atmosphere. Among the broader population of hot, directly imaged exoplanets and brown dwarfs studied over the past 2 decades, astronomers have found evidence for an even stranger range of cloud chemistry. Some of the hottest known exoplanets, with atmospheric temperatures exceeding 2000 degrees Fahrenheit, are believed to host clouds made of vaporized minerals, including iron and various silicate compounds, the same basic materials that make up rock here on Earth, existing as clouds only because the extreme heat keeps them in a partially vaporized state, capable of condensing into airborne particles, similar in physical principle to how water vapor condenses into clouds, just involving entirely different substances under entirely different conditions. Webb itself, in a separate set of observations made earlier in 2026, documented a planet roughly 700 light-years away with a genuinely bizarre daily weather cycle, in which clouds composed of vaporized minerals form predictably each morning as the planet's rotation brings a given region into more intense stellar heating, and then dissolve again each evening as that region rotates away from the heat, an alien weather pattern with no real equivalent anywhere in our own solar system. Against this backdrop of increasingly documented atmospheric exoticism, the confirmation of salt clouds on GJ504b fits into a broader, genuinely exciting pattern emerging across the field of exoplanet atmospheric science. The basic chemistry that produces familiar water clouds on Earth, condensation driven by temperature and pressure conditions specific to a given compound, turns out to be a universal principle that the galaxy applies to an enormous range of available chemical ingredients, producing cloud types and weather patterns across known and newly discovered worlds that range from the merely unfamiliar to the genuinely alien, each one a direct, readable consequence of the unique combination of temperature, chemistry, and physics present on that particular world. It is worth spending a little more time with the specific instrument and technique that finally cracked this mystery, because the engineering involved represents one of the more genuinely elegant solutions in modern observational astronomy. The fundamental challenge in directly imaging any exoplanet is what astronomers call contrast, the enormous difference in brightness between a star and any planet orbiting it. For a system like GJ504, the host star outshines its planetary companion by a factor that can run into the hundreds of thousands or millions, depending on the specific wavelength being observed. Trying to detect the planet's faint light is, as multiple researchers involved in this kind of work have described it, akin to trying to spot a firefly hovering directly next to a powerful searchlight from a great distance away. The searchlight's glare simply overwhelms any fainter source nearby, regardless of how sensitive your detector might otherwise be. Webb addresses this problem using coronagraphic instruments, devices built directly into its science cameras that function similarly in concept to the disk an observer might use to block the sun's overwhelming glare during a solar eclipse, allowing the much fainter solar corona to become visible. A coronagraph works by physically or optically blocking out the concentrated light from the central, bright source, in this case the host star GJ504, while still allowing light from any fainter objects in the surrounding field, including a planet like GJ504b, to reach the telescope's detectors relatively unimpeded. This is far more difficult to achieve in practice than the basic concept suggests, since stray light from the blocked star tends to scatter and diffract around the edges of any physical blocking mechanism, creating residual glare that can still overwhelm a faint planetary signal unless the coronagraph design is extraordinarily precise. Webb's coronagraphic capabilities, built into its near-infrared camera and other instruments, represent some of the most advanced starlight suppression technology ever deployed in space, refined through years of careful engineering and testing before the telescope's 2021 launch specifically, with observations like this one in mind. Beyond the coronagraph itself, the team analysing GJ504b also employed sophisticated post-processing techniques, mathematical and computational methods applied to the raw data after it has been collected, designed to further suppress any residual stellar light or instrumental noise that the coronagraph alone could not fully eliminate. These techniques often involve comparing observations of the target system against reference observations of other stars without known planetary companions, allowing astronomers to identify and subtract out patterns of light that are characteristic of the telescope's optics rather than genuine signals from the target system itself. The combination of Webb's space-based vantage point, free from atmospheric interference, its advanced coronagraphic hardware, and sophisticated computational data processing is precisely what allowed the team to accomplish in roughly 2 hours what a decade of dedicated ground-based effort, using some of the largest and most capable telescopes ever built on Earth's surface, had repeatedly and completely failed to achieve. There is a quietly important lesson sitting underneath the technical details of this story, one that connects directly to the broader pattern we have explored across many of these journeys through space together. GJ504b was never hiding. Its light has been reaching Earth continuously since long before any human telescope was capable of capturing it, carrying within it, the entire time, the complete chemical fingerprint of salt clouds, water vapour, methane, and metal enrichment that Webb finally read clearly in 2026. The planet did not change between 2013 and 2026. It did not develop new clouds or alter its fundamental chemistry over the intervening 13 years. What changed was entirely on our end, the instruments available to receive and interpret the message this distant world had been sending the entire time. This is a pattern worth recognizing, because it recurs again and again across the history of astronomy and across many of the specific discoveries we have explored together in these long-form journeys. The data was always there, embedded in the light. What was missing was the capability to read it. For over a decade, some of the largest, most sophisticated telescopes ever constructed on the surface of the Earth pointed at this single faint pink point of light and came back with nothing usable, not because the scientists operating them lacked skill or persistence, but because the fundamental physics of trying to observe something this faint and this cold from underneath an atmosphere that itself glows in the relevant wavelengths created a barrier that no amount of additional effort could overcome. It took a different kind of instrument entirely, one positioned beyond the atmosphere, cooled to temperatures near absolute zero, equipped with starlight suppression technology refined over years of careful engineering to finally close the gap between what existed and what could be observed. There is something worth sitting with in the fact that Baburaj and his team accomplished in 2 hours what previous astronomers, using some of the largest telescopes ever built, had failed to accomplish across entire nights of dedicated observation, repeated across more than a decade. This is not a story about earlier astronomers failing through any fault of their own. It is a story about the genuine, sometimes enormous gap between what we can imagine wanting to know and what our current instruments allow us to actually discover. A gap that narrows, sometimes dramatically and all at once, whenever a sufficiently capable new instrument finally comes online. GJ504b's salt clouds were always part of the universe's existing settled physics. They simply waited, patiently, for over a decade, for an instrument capable enough to finally notice them. To properly appreciate how unusual GJ504b is, it helps to place it alongside the small handful of other directly imaged exoplanets that astronomers have managed to photograph over the past 2 decades, since the contrast highlights exactly what makes this particular world such an outlier. The HR 8799 system, discovered in 2008, remains one of the most celebrated direct imaging achievements in the field's history. A young star roughly 129 light-years away, hosting at least 4 giant planets, all captured directly in a series of images that, when sequenced over subsequent years, actually show the planets visibly moving along their orbits, among the only direct visual confirmations of exoplanetary motion ever captured. These planets are considerably younger and hotter than GJ504b, with temperatures in the range of 1200 to 8100 degrees Fahrenheit, glowing with a much more vivid reddish thermal emission consistent with their relative youth, estimated at around 30 to 60 million years old, recently formed in cosmic terms and still radiating away substantial residual heat from their formation. Beta Pictoris b, another well-studied directly imaged planet around a star roughly 63 light-years away, similarly presents as a hot young giant planet, with a temperature around 1500 degrees Fahrenheit, again dramatically warmer than GJ504b's measured 550 degrees. Against this backdrop, GJ504b's coolness stands out starkly. It was, at the time of its 2013 discovery, explicitly noted as the coolest planetary mass object ever directly imaged, and even more than a decade later, after numerous additional direct imaging discoveries across the field, it remains among the coldest objects of its kind ever successfully observed and characterized. This extreme coolness is precisely why it took so much longer to properly study than its hotter, brighter cousins. A planet like one of the HR 8799 worlds, glowing brightly in infrared light due to its relative youth and correspondingly higher temperature, is simply easier to detect and characterize using ground-based instruments, even with all the challenges that direct imaging inherently presents. GJ504b's combination of extreme coldness and resulting faintness placed it at the very edge of what any pre-Webb instrument could meaningfully attempt, explaining both why the original 2013 detection was considered such a significant technical achievement in its own right, and why the subsequent decade of attempted follow-up characterization repeatedly came back empty-handed. The planet sat in a genuinely unique position within the broader catalogue of directly imaged worlds, distinctive enough in its basic properties to guarantee scientific interest, yet stubbornly resistant to detailed study using any technology available before Webb's launch. a combination that produced exactly the kind of decade-long high-profile mystery that made this year's breakthrough feel so significant to the broader astronomical community when it was finally announced. With the salt cloud mystery substantially resolved, attention within the research community is already shifting toward the questions this discovery has newly opened. Because resolving one puzzle about GJ504b has, in characteristic fashion for this kind of scientific work, generated several new and equally compelling ones. The most immediate open question concerns the planet's true age and mass, which remain formally unresolved despite the new spectral data. While the team's analysis leans toward favouring the older age estimate and correspondingly higher mass, placing the object closer to brown dwarf territory, a definitive resolution will likely require additional observational approaches beyond atmospheric spectroscopy alone. Astrometric measurements, which track an object's precise position and motion over time, can in principle help constrain a system's age and dynamical history through more indirect but complementary lines of evidence. An ongoing monitoring of the GJ504 system using both Webb and other instruments may eventually help narrow this persistent uncertainty. The metal enrichment finding similarly demands further investigation, confirming and more precisely quantifying just how enriched GJ504b's atmosphere actually is in heavy elements, and comparing that enrichment level against theoretical predictions from both the core accretion and gravitational instability formation models represents exactly the kind of detailed follow-up work that the broader exoplanet formation theory community will likely pursue using this. Newly available data, beyond GJ504b itself, the research team has explicitly signalled an interest in applying the same successful observational approach, Webb's coronagraphic imaging combined with careful spectral modelling that accounts for unexpected cloud chemistry, to other similarly cold, faint, directly imaged planetary mass companions that have resisted detailed characterization using ground-based instruments. Several other known directly imaged exoplanets and brown dwarfs occupy a similarly cold, faint region of parameter space to GJ504b. Objects that have been detected and roughly characterized, but never subjected to the kind of detailed atmospheric spectroscopy that just succeeded here. If Webb's success with GJ504b proves repeatable across this broader population, astronomers may be on the verge of substantially expanding our collective understanding of cold giant planet and brown dwarf atmospheres, a category of object that, by virtue of being so difficult to study, has remained comparatively undercharacterized relative to hotter, younger, brighter directly imaged worlds. There is also the broader question of what salt clouds specifically might tell astronomers about planetary formation and atmospheric evolution more generally, since their presence depends on a fairly narrow and specific combination of temperature and available chemistry. Understanding exactly how common salt clouds are across the broader population of cold planetary atmospheres, and what that commonality or rarity might reveal about the underlying chemistry of planet formation throughout the galaxy, represents precisely the kind of follow-up scientific question that a single, well-confirmed discovery like this one tends to generate, opening up an entire new avenue of inquiry that simply did not exist as a tractable research question before this year's breakthrough made it possible to ask with any real hope of finding an answer. It is worth zooming out one more time before we move toward a close, to place GJ504b within the truly vast scope of the broader search to understand worlds beyond our own solar system, a scientific endeavour that has expanded almost unrecognisably within a single human lifetime. The first confirmed detection of a planet orbiting a sun-like star other than our own came in 1995, when astronomers identified 51 Pegasi be a hot, Jupiter-sized planet orbiting remarkably close to its host star, a discovery that earned its researchers a Nobel Prize and effectively launched the modern era of exoplanet science. At the time, the very existence of planets around other stars, while long suspected, had never been definitively confirmed. 3 decades later, the confirmed exoplanet catalogue has grown to include more than 6,000 worlds, a number that continues climbing steadily as missions like NASA's Transiting Exoplanet Survey satellite and ground-based survey programs continue scanning the sky. Among this enormous and rapidly growing catalogue, the small number of planets that have actually been directly imaged, fewer than 100 even now, more than a decade after GJ504b's discovery, represents a tiny but disproportionately scientifically valuable subset, precisely because direct imaging offers the kind of atmospheric access that indirect detection methods generally cannot easily provide. NASA's upcoming Nancy Grace Roman Space Telescope, expected to launch in September 2026, is specifically designed, in part, to dramatically expand the catalogue of known exoplanets through a different kind of wide-field survey, potentially identifying as many as 100,000 new worlds through a combination of detection techniques, including gravitational microlensing, a method that detects planets by observing how their gravity briefly distorts and magnifies the light of a more distant background star as the planetary system passes in front of it from our perspective. While Roman's primary detection methods will not directly image these new worlds in the way Webb imaged GJ504b, the sheer scale of the expected catalogue expansion will likely identify numerous additional candidates suitable for follow-up direct imaging and spectroscopic study using Webb and future instruments, potentially extending exactly the kind of detailed atmospheric characterization just demonstrated on this one strange pink world to a substantially larger population of similarly distant, similarly enigmatic objects. The story of GJ504b, in this broader context, represents both a genuine scientific achievement in its own right and a preview of what becomes possible as humanity's collective toolkit for studying worlds beyond our own solar system continues to expand. A single planet, photographed in 2013, partially understood for over a decade, finally read clearly in 2026, stands as one small but genuinely illuminating chapter within a far larger ongoing story, the patient, decades-spanning human project of learning to see, and eventually to understand the almost unimaginably vast population of worlds scattered throughout our galaxy. Let us build some context around the specific numbers in this story, the way these long, slow journeys tend to do, because the figures involved deserve more than a passing mention. 57 light-years. That is the distance separating us from GJ504. Light, moving at roughly 186,000 miles every single second, the fastest velocity that exists anywhere in the universe, takes 57 years to cross that gap. The light Webb analysed in its 2-hour observation left GJ504b's atmosphere 7 years before arriving at the telescope's detectors, meaning the salt clouds Webb identified existed in that configuration more than half a century ago, and the planet we now understand in such fine detail may have shifted and changed in ways both subtle and significant during the decades that light spent, crossing the gap between its origin and our observation of it. 44 astronomical units. That is the minimum projected separation between GJ504b and its host star, a distance comparable to the gap between our own Sun and Pluto. At that remove, even a Sun-like star provides only a faint glimmer of warmth, meaning whatever heat radiates from this distant planet comes overwhelmingly from within, the residual thermal signature of its own formation, slowly fading across timescales that may span anywhere from tens of millions to several billion years, depending on which age estimate eventually proves correct, 550 degrees Fahrenheit. The planet's measured temperature, hot by the standards of everyday human experience, comparable to the inside of a bread baking oven, yet dramatically, strikingly cold by the standards of directly imaged exoplanets, most of which register temperatures between 1000 and 2000 degrees Fahrenheit. 2 hours, the total observation time Webb required to capture a clean, detailed spectrum of this planet's atmosphere, definitively succeeding where more than a decade of accumulated ground-based observation using some of the largest and most technologically advanced telescopes ever constructed on the surface of the Earth had completely and repeatedly failed. And 13 years. The span between the planet's initial direct imaging discovery in 2013 and the publication of its first successful atmospheric spectrum in June of 2026. 13 years during which this strange pink world sat in the published astronomical literature as a confirmed but stubbornly unexplained anomaly, its true nature debated, its atmospheric chemistry a mystery, its very classification as planet or brown dwarf left formally unresolved. 13 years is a substantial span within the relatively young field of direct exoplanet imaging itself, which has existed in its modern, technically mature form for barely 2 decades. For a third of that field's entire working history, this single object sat as one of its most persistent and well-known unsolved puzzles, finally yielding its secrets not through any single dramatic breakthrough in theory, but through the patient, incremental arrival of a sufficiently capable instrument built specifically to extend human observational reach beyond what had previously been achievable, finally turned toward this one stubborn, strange, beautiful pink point of light. Hold all of these numbers together for a moment. 57 light-years of distance. 44 astronomical units of separation from a sun-like star. 550 degrees of measured heat. 2 hours of decisive observation. 13 years of accumulated uncertainty. Each number, on its own, is simply a measurement. Together they tell the complete shape of a single scientific story, from first faint detection to final, detailed understanding, a story that took place almost entirely without any of the people experiencing it ever once leaving the surface of the Earth. There is something worth dwelling on about how much scientific information can be extracted from something as simple sounding as a planet's colour, because GJ504b's story is, at its heart, a demonstration of just how much physics and chemistry can be encoded in the specific wavelengths of light an object happens to emit or reflect. Colour, to the human eye, feels like a simple, immediate perception, the kind of basic sensory information we process effortlessly and rarely think to question. But to an astronomer studying a planet 57 light-years away, colour is data, a direct and quantifiable signal carrying information about composition, temperature, atmospheric structure, and physical processes that would otherwise be completely inaccessible. Every wavelength of light that reaches a telescope's detector has been shaped by its interaction with matter, whether that matter is the planet's own internal heat source generating the light in the first place, or the atmosphere the light passes through on its way to becoming observable. By carefully measuring exactly how much light arrives at each specific wavelength, building what astronomers call a spectrum, researchers can work backward from the observed pattern to infer the physical conditions that must have produced it. This is precisely the forensic process that finally cracked GJ504b's mystery. The planet's overall pink colour had been known since 2013, but a single colour measurement, however striking, cannot by itself reveal the detailed atmospheric chemistry producing that colour. It took Webb's far more detailed spectroscopic data, breaking the planet's light apart into many individual wavelength measurements rather than a single overall color impression. To reveal the specific molecular signatures of water vapor, methane, carbon dioxide, and ammonia, and then, through careful modeling of how those signatures were being distorted, the previously invisible presence of salt clouds sitting in the upper atmosphere. This same basic principle, that light carries detailed, decodable information about the physical conditions that produced or shaped it, underlies essentially every discovery explored throughout these long-form journeys into space. It is how astronomers determine the chemical composition of stars billions of light years away. It is how they measure the expansion rate of the universe by analysing the stretching of light from distant galaxies. It is how they identified water vapour and other molecules in the atmospheres of exoplanets light years from Earth, and it is precisely the technique that, applied with sufficient precision and sensitivity to GJ504b's faint pink glow, finally resolved a mystery that had persisted, unsolved, for more than a decade. Light is, in this sense, perhaps the most information-dense substance the universe provides freely to anyone capable of building an instrument sensitive enough to properly read it, carrying within its specific pattern of wavelengths an extraordinarily detailed and decodable record of the physical conditions, however distant or exotic, that shaped its journey from source to detector. It is worth taking a moment to recognize the scale of collaborative human effort that sits behind a discovery like this one, because the published research paper documenting GJ504b's salt clouds carries an author list extending to more than 24 names, scientists drawn from Northwestern University, the Space Telescope Science Institute, and a long roster of additional research institutions spanning the broader astronomical community. This kind of large, multi-institutional collaboration has become the standard model for cutting-edge observational astronomy in the era of major space telescopes, reflecting the genuinely interdisciplinary expertise required to take a project like this one from initial concept through to a fully validated, peer-reviewed scientific result. Securing observing time on Webb in the first place requires winning a competitive proposal process in which research teams from around the world submit detailed scientific justifications explaining why their particular target deserves a share of the telescope's extremely limited and highly sought-after observing schedule. Webb's total observing time each year is allocated through this proposal system, with demand for telescope time consistently and dramatically exceeding the hours actually available, meaning the team's successful proposal to study GJ504b had to compete against many other scientifically compelling projects for a relatively small allocation of the telescope's overall schedule. Once observing time was secured and the roughly 2-hour observation completed, the actual scientific work was only beginning. The team needed to process the raw data Webb returned, correcting for instrumental effects and residual stellar contamination, before they could even begin attempting to model and interpret the resulting spectrum. The process of testing different atmospheric models, including the eventual successful incorporation of salt clouds into their simulations, required extensive computational modeling, comparing theoretical predictions against the actual observed data across many different candidate scenarios, before arriving at the configuration that finally produced a physically consistent fit. This entire process, from securing observing time through to final publication in the Astronomical Journal on June 18, 2026, represents months of dedicated work by a substantial team of researchers, building on more than a decade of prior research by other scientists who had attempted and failed to crack this same mystery using less capable instruments. Aneesh Baburaj, the study's lead author and a postdoctoral associate at Northwestern University's Center for Interdisciplinary Exploration and Research in Astrophysics, has spoken publicly about the genuine surprise the team experienced upon finally seeing results that aligned with what theory had long predicted but no one had ever actually confirmed. That combination, rigorous theoretical prediction made over a decade earlier, finally validated through painstaking observational work using an instrument that did not even exist when the original theoretical proposal was first published, represents science functioning exactly as it is meant to, patient, collaborative, and ultimately, after enough persistence and the arrival of sufficiently capable tools, genuinely productive. There is a final, broader thread worth following before we move toward a close, concerning what discoveries like this one mean for the larger, more emotionally resonant question that drives so much of exoplanet science in the public imagination, the search for worlds that might host life. GJ504b itself is almost certainly not a candidate for life as we understand it. As a massive gas giant or brown dwarf, lacking any solid surface and existing under atmospheric conditions of extreme pressure and temperature variation, far beyond anything compatible with known biological chemistry, it sits firmly outside the category of worlds astronomers consider potentially habitable. But the techniques demonstrated in successfully characterizing its atmosphere carry direct and significant relevance to that broader search. Because the fundamental challenge, isolating a faint planetary signal from the overwhelming glare of a host star, and then extracting a detailed chemical spectrum from that faint signal, is precisely the same challenge that future efforts to characterize potentially habitable, Earth-sized rocky planets must eventually overcome in an even more extreme form. A rocky Earth-sized planet is dramatically smaller and fainter than a Jupiter-scale gas giant like GJ504b, meaning the contrast problem between planet and host star becomes correspondingly more severe, and the technical challenge of isolating that planet's light for detailed spectroscopic study becomes correspondingly more difficult. NASA's planned Habitable Worlds Observatory, a future flagship mission still in early planning and design stages, is being specifically conceived around exactly this challenge, with the explicit scientific goal of directly imaging Earth-sized rocky planets around nearby Sun, like stars, and analysing their atmospheres for potential biosignatures, chemical indicators that might suggest the presence of life. Recent modelling work published in 2026 has already begun examining how confidently such a future mission might be able to identify genuine biosignatures in the atmosphere of a distant ancient Earth-like world, essentially asking how well our detection techniques would perform if pointed at a planet similar to our own at various points in its multi-billion-year history. The successful demonstration of Webb's coronagraphic capabilities on GJ504b, extracting a clean, detailed, scientifically rich spectrum from one of the coldest, faintest directly imaged planetary mass objects ever studied, serves as a genuinely meaningful proof of concept for the broader technological trajectory the field is now pursuing. Each successful application of these starlight suppression and spectroscopic techniques to increasingly challenging targets, whether cold gas giants like GJ504b or, eventually, much smaller and fainter rocky worlds, represents an incremental but genuinely cumulative expansion of what becomes observationally possible. The pink planet's salt clouds, in this sense, represent more than just the resolution of one specific decade-long mystery. They represent another confirmed data point in the steadily advancing technological capability that will, eventually, allow humanity to point similarly sophisticated instruments at smaller, more distant, more genuinely Earth-like worlds and ask, with rigour and precision rather than speculation, whether anything is looking back. Let us spend a moment considering what the future likely holds for GJ504b itself, since giant planets and brown dwarfs alike follow a slow, predictable trajectory of gradual cooling across timescales that dwarf anything in human experience. Whatever its true age and precise mass eventually prove to be, GJ504b is, in either scenario. An object that began its existence considerably hotter than it currently registers, radiating away the substantial heat generated either during a relatively recent planetary formation process or, in the alternative scenario, during its initial gravitational collapse as a brown dwarf billions of years ago. This cooling process is gradual, predictable, and essentially irreversible, governed by well-understood physics relating an object's mass, composition, and current temperature to the rate at which it loses heat to the surrounding cold of space. If the younger age estimate proves correct, placing the system at a mere 21 million years old, GJ504b would still be in a relatively early phase of this cooling trajectory, having radiated away only a modest fraction of its total formation heat, with billions of years of continued gradual cooling still ahead of it. Under this scenario, the planet would continue to slowly dim and cool across the coming eons, its temperature dropping further below the already cold 550 degrees Fahrenheit currently measured, its salt clouds potentially shifting in altitude and character as the specific temperature range required for salt condensation moves correspondingly with the planet's overall cooling atmosphere. If instead the older age estimate proves correct, placing the system at several billion years old, GJ504b would already be relatively far along this same cooling trajectory, having spent billions of years gradually radiating away its formation heat to reach its current, already quite cold temperature. Under this scenario, the planet's future holds a continuation of the same slow process, but starting from an already advanced stage, with the planet destined to grow gradually colder and dimmer over the following billions of years, potentially eventually becoming too faint and too cold for any future instrument, however advanced, to meaningfully characterize using techniques similar to those just successfully employed by Webb. In either scenario, GJ504b's salt clouds, the very feature that took more than a decade to discover and confirm, are themselves a temporary, if long-lasting, atmospheric feature, tied to a specific window of temperature that the planet currently occupies, a window that will eventually close as the world's slow, patient cooling continues across timescales that make the 13 years between its discovery and its eventual atmospheric characterization look, by comparison, like the briefest possible instant. Before we move toward a close, let us build one final piece of perspective, the kind these long, slow journeys tend to end with, because there is something genuinely worth sitting with in how this particular story unfolded. In 2013, a team of astronomers using one of the largest telescopes ever built on the surface of the Earth captured a faint, persistent point of pink light next to a sun like star 57 light-years away. They could measure its rough position, estimate its mass within a wide range of uncertainty, and note its strikingly unusual colour. That was the entire extent of what was knowable at the time. For the following 13 years, that single faint point of pink light sat in the published scientific literature as one of the field's most persistent and well-known mysteries, its true nature debated across dozens of papers, its atmospheric chemistry entirely inaccessible to direct study, its fundamental identity as planet or brown dwarf left formally unresolved despite years of accumulated theoretical work attempting to constrain the possibilities using whatever indirect evidence could be gathered. Then, in roughly 2 hours of observation time, using an instrument positioned 1 million miles from Earth, cooled to near absolute zero, equipped with starlight suppression technology refined over years of careful engineering, that same faint point of pink light finally yielded a complete, detailed, scientifically rigorous spectrum revealing water vapour, methane, carbon dioxide, ammonia, an unusual enrichment of heavy elements, and, most strikingly, the first direct confirmation anywhere of theorized salt clouds that had existed only as an untested hypothesis in the scientific literature for more than 15 years before this observation finally confirmed them. 13 years of accumulated mystery resolved in 2 hours by an instrument built specifically to extend human observational capability beyond what had previously been achievable. This is not a story about earlier efforts failing through any lack of skill or persistence. It is a story about the genuine, sometimes dramatic gap between what we can imagine wanting to know and what our current tools allow us to actually discover. A gap that can persist for years or decades, seemingly permanent, until the right instrument finally arrives and closes it, sometimes all at once, revealing in a single observation what generations of careful, patient, repeatedly unsuccessful effort had been unable to extract from the same faint point of light the entire time. GJ504b's colour was never a mystery to the universe itself. The salt clouds shaping that colour have been there, doing exactly what salt clouds do, for as long as the planet's atmosphere has existed in its current state. The mystery existed entirely on our side of the 57 light-year gap, a temporary solvable limitation of human technology rather than any genuine uncertainty in the underlying physics of this strange, distant, beautifully pink world. It is worth taking one final close look at the specific chemistry involved here, because salt, in the everyday sense most people understand the word, refers to ordinary table salt, sodium chloride, the familiar white crystalline compound found in kitchens worldwide. In the broader chemical sense that astronomers use when discussing planetary atmospheres, the term salt refers to a much wider category of compounds, generally formed when a metal element bonds with a non-metal element in a stable crystalline structure. The specific salt compounds theorized and now confirmed to exist in GJ504b's atmosphere likely include sodium sulfide and potassium chloride, among other possible alkali metal compounds, substances that remain in gaseous form at higher temperatures deep within the planet's atmosphere, but begin condensing into solid or liquid particles once the surrounding gas cools sufficiently as it rises, toward the upper atmospheric layers. This condensation process, fundamentally, mirrors the basic physics of cloud formation anywhere in the universe, a substance existing as vapor under one set of temperature and pressure conditions, then transitioning into a condensed particulate form once those conditions shift past a critical threshold specific to that substance's particular chemistry. What makes this discovery genuinely significant, beyond simply confirming a specific compound's presence in one particular planet's atmosphere, is what it reveals about the broader chemical inventory available within cold giant planet atmospheres generally. The presence of significant quantities of sodium and potassium, the metal elements that combine to form these salt compounds, in a planet's atmosphere connects directly back to the broader metal enrichment finding discussed earlier, since these alkali metals are themselves part of the same category of heavier elements whose unusual abundance in GJ5004b points toward the core accretion formation scenario. The salt clouds, in other words, are not an isolated curiosity disconnected from the rest of the planet's story. They are a direct, visible, observationally confirmable consequence of the same underlying chemical enrichment that raises deeper questions about how this strange, distant world actually formed in the first place. Theoretical models predicting salt cloud formation in cold planetary atmospheres, first proposed more than 15 years before this confirmation, specifically required atmospheres enriched in these particular alkali metals beyond what a purely hydrogen and helium composition would provide, meaning the successful detection of salt clouds on GJ504b serves simultaneously as confirmation of a long-standing theoretical prediction about cloud chemistry, and as independent supporting evidence for the planet's unusual metal-rich composition. Two previously separate lines of theoretical reasoning converging, in this single observation, into a single coherent and mutually reinforcing picture of an atmosphere considerably stranger and more chemically complex than anyone could have confidently described, before Webb's 2 hours of careful, patient observation finally made it visible. GJ504b's story fits a broader and genuinely recurring pattern in the history of astronomy, one worth recognizing, because it reframes how we should think about any unsolved mystery currently sitting in the published scientific literature. Time and again, across the history of this field, a genuine puzzle gets identified, generates years or even decades of speculation and failed attempts at resolution, and then finally yields, often quite suddenly, once a sufficiently capable new instrument or technique becomes available. The accelerating expansion of the universe sat as an open theoretical possibility for decades before two independent teams studying distant supernovae in the late 1990s finally produced definitive observational evidence, work that earned a Nobel Prize and fundamentally reshaped cosmology. The existence of gravitational waves, predicted by Einstein's general relativity in 1916, remained entirely theoretical for nearly a full century before the Laser Interferometer Gravitational Wave Observatory finally achieved the staggering technical precision required to directly detect them in 2015, confirming a century-old prediction in a single dramatic observation. Pluto's now famous heart-shaped nitrogen ice plain remained completely unknown and unimaginable until NASA's New Horizons spacecraft finally provided humanity's first close-up images during its 2015 flyby, resolving in a matter of hours what had been an unanswerable question for the entire preceding history of telescopic observation of that distant world. In each of these cases, and in countless others scattered throughout the history of this field, the underlying physical reality never changed. The universe's expansion was always accelerating. Gravitational waves were always rippling through space-time exactly as Einstein's equations predicted. Pluto's surface always held that distinctive heart-shaped plane. What changed in every single case was the arrival of an instrument finally capable of detecting and characterizing a phenomenon that had been there, patiently the entire time, waiting for technology to catch up with curiosity. GJ 504b's salt clouds belong squarely within this same pattern. They existed, shaping the planet's light in precisely the way Webb eventually measured. For as long as the planet's atmosphere has existed in its current chemical and thermal state, almost certainly for many millions of years at minimum. The 13-year gap between the planet's initial discovery and the eventual confirmation of its atmospheric chemistry was never a gap in the universe's underlying physics. It was a gap in human technological capability. A gap that, like so many before it across the broader history of this field, eventually closed, not gradually, but suddenly, completely, in the span of a single well-designed 2-hour observation using an instrument built specifically to extend the boundaries of what had previously been observationally possible. There is something worth carrying with you as we close tonight about what it actually means for a mystery to last 13 years and then dissolve in the space of a single 2-hour observation. Somewhere out there, 57 light-years from where you are lying right now, a strange, cold, pink world continues its slow, patient orbit around a sun-like star 44 astronomical units out, roughly where Pluto would sit in our own solar system, its salt clouds drifting silently through an atmosphere of hydrogen and helium, scattering the planet's own internal glow into that distinctive dull magenta colour that first caught astronomers' attention back in 2013. It does not know it has a name. It does not know it has been the subject of more than a decade of failed observation attempts, dozens of published scientific papers, and an eventual celebrated breakthrough using a telescope positioned 1 million miles from the world where the scientists studying it actually live. It simply exists, exactly as it has existed for millions or billions of years, depending on which age estimate eventually proves correct, radiating away its formation heat at the same slow, steady pace it always has, indifferent to whether anyone back on a small blue planet 57 light-years away has finally managed to read the chemical fingerprint hidden in its faint, ancient light. And yet, despite that vast indifference, despite the decade of dead ends and failed observations and persistent uncertainty, a team of patient, careful scientists kept the question alive. They kept proposing new observations. They kept refining their models. They kept waiting for an instrument capable enough to finally close the gap between what they wanted to know and what they were actually able to observe. And when that instrument finally arrived, when Webb's coronagraph and its million-mile remove from any atmospheric interference finally made the impossible possible, the answer came quickly, decisively, and in a form richer and stranger than anyone had specifically predicted. Salt clouds confirmed for the first time anywhere exactly where theory said they might exist, but where no one had ever actually managed to see them. This is perhaps the quiet lesson sitting underneath tonight's entire story. Some mysteries are not permanent. They simply require patience and the right tool, and a willingness to keep asking the same question for as long as it takes for the universe to finally answer clearly. The pink planet kept its secret for 13 years, not because the secret was unknowable, but because the secret was waiting, the entire time, for someone with the right eyes to finally come looking. Sleep well tonight, knowing that even the strangest, most stubborn mysteries in the night sky are, eventually, patient enough to be solved. Good night.